Swayam Prabha. Digital India. Educated India.
In the next two lectures, let us see some practical applications whose governing differential equations are of the form of the general two dimensional boundary value problem, for which we already derived finite element equations. And for each of these applications that we are going to look at, the basic variables and equations. Let us look at first the basic variables and associated equations corresponding to that application, and these variables are then interpreted in the context of variables in the general two dimensional boundary value problem, and then we will derive the finite element equations and finite element solutions. We will try to obtain using the derived finite element equations. So, as a part of this, let us start with torsion of prismatic bars. Torsion of a long prismatic bar, that is bar with same cross section throughout its length, can be formulated as two dimensional problem using two approaches. One is either stress function, one is stress function approach and other is warping function approach. But whatever equations that we are going to derive, we will stick with stress function approach. So, this figure shows variables associated with the torsion problem. U as a function of x y, v as a function of x y are the displacements in x and y directions. X y directions, the axis x y axis and z axis are clearly marked in the figure, and u and v are the displacements in x and y directions, and w is the displacement in z direction, which is oriented along centroidal axis of the bar. For deriving the governing equations, linear elastic behavior and small displacements are assumed. Besides linear elastic behavior, small displacements, the following are the key assumptions. Displacements u and v are related to the angle of twist. Angle of twist is indicated in the figure, and the displacement along x direction and displacement along y direction are related to angle of twist theta. Via these two equations, only shear stresses are present at any plane cross section along the bar axis. That means two stress components of interest are tau xz, which is going to be same as tau zx, and tau yz, which is going to be same as tau zy. With these assumptions, the governing differential equations can be derived as follows using strain displacement relation shape. We can get the strains in terms of displacements, and these are the relations. Substituting, we already know displacements along x and y directions, that is u and v in terms of theta, z, or theta, substituting the assumed displacement field u is equal to minus theta z y, v is equal to v is equal to theta z x. Substituting these, the previous strains can be expressed in terms of angle of twist theta. So, once we have strains, we can calculate stresses using Hooke's law. Use Hooke's law to express stresses in terms of displacements. Based on Hooke's law, we get this relation between shear stress and shear strain, and substituting the gamma xz that we just obtained into this equation, we get in terms of angle of twist. The other stress component is this one. Write the equilibrium equations by considering equilibrium of forces acting on a differential element in the cross section. We get this equation, and now imagine a stress potential such that it satisfies these equations, and if we can, or if we are able to find such a stress potential which satisfies these two conditions, then equilibrium will automatically satisfied, which is shown here, because when we substitute these stress components, we notice that equilibrium equation is automatically satisfied. So, basically the problem is reduced to finding a stress function from stress strain law. We know that stresses are given by these two equations, which in turn can be related to the stress potential. To eliminate W, differentiate the first equation with respect to y, the second equation with respect to x, and subtract two equations from each other. Subtracting the second equation from the first, we get the governing differential equation in terms of stress functions. And the appropriate boundary conditions from the assumptions made regarding stress distribution are that there must be no resultant shear stress on the boundary. So, this is the governing differential equation. So, now we need to look at the boundary conditions. So, boundary conditions will be derived based on the condition no resultant shear stress, there is no resultant shear stress on the boundary, that is tau xz times nx plus tau yz times ny is equal to 0, where nx and ny are nothing but the components of outer normal, which is shown in the figure along x and y directions, or in other words nx and y are the direction cosines of outer normal to the surface. Since we know the relation between the shear stress components and the stress potential, we can express this equation in terms of stress potential. For that, noting that outer normal has components n x and y, and n x is given by cos alpha. Cos alpha can be calculated based on the figure that is shown there, that is dy over ds, and ny is equal to sin alpha, which is given by minus dx over ds, where ds is a small element of idealized boundary. So, substituting the stress components in terms of the shear stress components in terms of stress potential, and also substituting n x n y in terms of dy ds and dx ds, the boundary condition in terms of stress potential phi can be expressed by considering differential element along the surface as shown in the figure. No stress requirement can be expressed as, here basically n x and y are substituted, and substituting stress components in terms of stress potential, finally we get this equation, that is partial derivative of stress potential with respect to S is equal to 0. Basically, the meaning of partial derivative of stress potential with respect to S is equal to 0 means stress potential phi must be constant on the boundary, the actual numerical value can be arbitrary, usually a value of 0 is assigned to phi on the boundary. So, basically the torsion problem is governed by the following boundary value problem. This is the governing differential equation with, that is second derivative of phi with respect to x plus second derivative of phi with respect to y plus 2 times shear modulus times angle of twist is equal to 0 with with stress potential, with stress potential phi is equal to 0 on the boundary. So, this is the problem statement. So, basically to repeat that, this is the problem statement. So, we can derive the finite element equations for the torsion problem by comparing with a general 2 dimensional boundary value problem. The equations corresponding to general 2 dimensional boundary value problem. So, basically let us go back and see what we have done for 2 dimensional boundary value problem. The 2 dimensional boundary value problem statement is like this: partial derivative of kx times dou t over dou x with respect to x plus partial derivative of ky times dou t over dou y with respect to y plus p times t plus q is equal to 0 over a domain A subjected to these boundary conditions, essential boundary condition and natural boundary condition can be specified. we used, if you recall, we used Galerkin criteria and we derived the finite element equations. The Galerkin criteria corresponding to the general 2-dimensional boundary value problem can be written like this, and we can use Green's theorem on the first two terms. Green's theorem is summarized here, integration by parts in 2 dimensions. These are the two formulas that we can use to simplify the previous equation. So, using these two formulas, the previous equation, here n x and y have same meaning as what we discussed, direction, cosines of boundary, normal. So, using these two equations, the first two terms of the earlier equation can be written in this manner, and if you see the second integral, integral over S2, based on the explanation that is provided earlier when we are looking at the derivation of the finite element equations for general 2-dimensional boundary value problem, this equation can be further written in matrix form like this, and the integral, the term with integral over S2 can be replaced with the term with integral over S as shown in the second equation for the reasons that I explained to you earlier. So, basically using Galerkin criteria we get this in terms of derivatives of shape functions Bx, By are the matrices consisting of derivative of shape functions, and n is matrix consisting of finite element shape functions. And this equation, the last equation, can further be simplified by substituting the natural boundary condition that is provided. So, substituting this natural boundary condition into the previous equation can be further written or further simplified, and the complete element equations can be written as follows, where each of these components kx, ky, kp k alpha, r beta, r q are as defined here, and it must be kept in mind that k alpha, r beta are added only for those elements for which natural boundary conditions are specified. We discussed all this when we looked in detail the derivation of finite element equations for general 2-dimensional boundary value problems. So, given the governing differential equation corresponding boundary conditions for a particular application, the first job is to identify what are these kx, ky, pq coefficients, and then we can easily assemble the finite element equations corresponding to that particular element if you know the shape functions and derivative of shape functions. The equations associated with essential boundary conditions must be removed from the global equations before solution. Since the shape functions are very simple for linear triangle, it is possible to carry out all integrations in closed form assuming kx, ky, pq are constant over element to get element equations in an explicit form as follows. So, kx for linear triangle element is given by this, which can be further simplified, and similarly ky and Kp, and to simplify the terms in Kp, since shape functions are not constant, we require to use some formula. Fortunately, following simple formula is available for integrating shape functions over element. So, this is the formula which you can use to simplify the terms in Kp, and where alpha, beta, gamma are the integer powers of shape functions n1, n2, n3. A is the area of triangle, and the symbol exclamation denotes factorial, and using integration formula the terms in Kp can be evaluated as follows. One of the term is shown here, and one more term, and similarly other terms can be evaluated. Evaluating other terms in a similar manner, the matrix Kp can be written as follows, and Rq, substituting the finite element shape functions, we can simplify this, and we can here also we can use this formula if required. The values of some of the terms are shown here, therefore Rq is given by this. And since the boundary of the element consists of 3 straight lines, that is, since we are dealing with linear triangle element, the integrals k alpha r beta must be evaluated separately for each side of triangle, and the details are shown for one of the sides. Integration along side 1, 2, first we require to find length of side, and then k alpha can be written like this, and we require to know which shape functions are going to be non-zero. Along side 1 to n3 is going to be 0, n1 n2 are linear functions of S local coordinate system. So, using one dimensional Lagrange interpolation formula, using like one dimensional Lagrange interpolation formula, the trial solution along side 1 2 can be written as follows, and substituting this into k alpha, we get, or we can approximate k alpha along side 1 2, and simplified form of k alpha is given. Here alpha is assumed to be constant. If alpha is not constant, then we need to include that inside the integral, and then you adopt numerical integration procedures. Similarly, R beta along side 1 2, the details are shown here, and what about other sides? For other sides like side 2 3 and 3 1, integrals can be evaluated in a similar manner, and finally we can get equations for all sides. In fact, only one, and while doing this, the only thing that differs for each of the sides is the placement of zeros in the shape function matrix N. It is easy to verify that for sides 2 3 and 3 1, the corresponding k alpha r beta are like this. So, this is what we have done when we are deriving finite element equations for general 2 dimensional boundary value problem. So, now we can use these finite element equations and identify what are the corresponding kx, ky, pq, the torsion problem, torsion of prismatic bars, and we can easily get the finite element equations. So, this is the governing differential equation subjected to the boundary condition that stress function is equal to 0, the essential boundary, and comparing this with whatever we just briefly reviewed, comparing this equation with the general 2 dimensional boundary value problem, we see that kx ky is equal to 1, p is equal to 0, q is equal to 2 g theta. So, we can easily substitute this information into the equations that we have just seen, and we can get the equations corresponding to torsion of prismatic bars. Triangular element equations for torsion can be written using the general formula as follows. We should also keep in a note about these coefficients B1, B2, B3, what they mean, and if all the 3 coordinates, if all the coordinates of 3 nodes of linear triangular element are known, you can easily calculate what is B1, B2, B3 and also C1, C2, C3, and A is the area of triangle, area of the element, triangular element, and phi 1, phi 2, phi 3 are the unknown stress functions at the element nodes. So, in this problem of solving torsion of prismatic bars, we are basically solving for the stress functions. Once we know the nodal values of stress functions phi, we can calculate what are the stress components, shear stress components. Once the nodal values are known, stresses can be calculated using element shape functions. So, the stress function or stress potential value at any point inside the element can be interpolated using this equation, and taking derivative of that we get the stress components. And what about torque calculations? In practical applications, the torque required for unit angle of twist is frequently of interest. Torque can be calculated from the phi value by considering differential element as shown in the figure below. And to develop the relation, we can take moments about origin, we get this equation, and the total torque is given by integrating this over the entire area of cross section. So, total torque is given by this, and this area integral can be expressed in terms of surface integral using Green's theorem. Using Green's theorem, the integral can be expressed in terms of surface integral. We have already looked at Green's theorem formulas. So, using those we can write this equation, and we also know that the essential boundary condition states that stress potential phi is equal to 0 on the boundary. So, the first two terms, which are basically integrations over the surface, are going to disappear. So, therefore, total torque is given by this And how to calculate this using finite element, the nodal values that we obtained using finite element. In finite element calculations, torque is computed over each element and then summed, that is we will calculate torque for each of the elements and then sum up over all the elements, then we get the total torque. And for that we require to find what is the torque over each element. Torque over each element is given by this shape functions associated with that particular element. And simplifying this equation, for linear triangular element, we know that n1 integrated over entire area of triangle, n2 integrated over entire area of triangle, n3 integrated over entire area of triangle is equal to a over 3. So, the previous equation for linear triangle element simplifies to this one. So, total torque is basically we need to add over all elements, for each element it is 2/3 area times or 2 times average stress function, stress potential value. So, now let us apply these equations to solve a problem. So, the problem statement is like this: determine the stress distribution in a square bar shown in figure below. So, cross section of the bar is square, the dimensions of the bar is, so the cross section of bar is square and the dimensions of cross sections are, cross section is indicated 4 centimeter by 4 centimeter, and we can notice that there is symmetry. So, because of symmetry only a quarter of this cross section needs to be modeled, the corresponding the values of shear modulus and also angle of twist are given here in the problem statement. So, we will model only the quarter portion that is shaded in the figure. The corresponding boundary conditions are also indicated. Phi is equal to 0, stress potential is equal to 0 on the boundary, and also derivative of stress potential is 0 on the sides over which symmetry boundary conditions are applied. So, now let us take the quarter model and discretize that using 4 elements, 4 linear triangle elements. The discretization is shown with element numbers 1, 2, 3, 4, and also nodes are numbered and corresponding coordinates in xy coordinate system for each of the nodes is indicated. So, element 1 comprises of nodes 1, 2, 5, element 2 comprises of 1, 5, 3, element 3 comprises of 2, 5, 4, element 4 comprises of 3, 5, 4. And since each of the triangle elements are of same size, the element equations are going to be identical for each of these element stiffness equations are going to be identical for each of these elements. And substituting the values of the coordinates into this equation, we can actually get element equations for each of the elements. All elements are identical and their equations can be written as follows. And here phi 1, phi 2, phi 3 are in the local coordinate system. Locally the node is 1, locally these nodes 1, 2, 3 can be different globally depending on the local to global node numbering mapping. So, all elements will have identical equations. So, now let us look at where the contribution from element 1 goes in, contribution from element 2 goes in, and element 3 and element 4 goes in into the global equation system. For that we require to take a note of global node numbers and the corresponding local node numbers, and also please note that in this problem, that is torsion of prismatic or torsion of square bar, at each node we have only one unknown, that is stress potential value. So, the contribution from element 1 goes into the locations depending on the numbering sequence 1 to 5 rows and columns of the global equation system, and the locations in the global equation system is shown in the table or in a matrix form. Similarly, for element 2 the contribution goes in 3, 5, 1 sorry 3, 1, 5 rows and columns of the global equation system, and element 3 contribution goes into 2, 4, 5 rows and columns of the global equation system. Element 4 contribution goes into 4, 3, 5 rows and columns of the global equation system. So, with that understanding, assembly of equations gives us this as the global equation system, final global equation system. And we know that stress potential is equal to 0 on the boundary, that is along nodes 2, 4 and 3. So, substituting the essential boundary condition, that is stress potential value at nodes 2, 3, 4 is equal to 0, we will be left with only the first and last equations, and solving those two equations we get phi 1 and phi 5 as these values. Once we have the stress potential, we can easily calculate stresses. So, solution of phi 1, phi 5 are these. So, stress calculations, element 1 substituting the derivatives of shape functions and the nodal values corresponding to element 1, we get shear stress component tau x z as 0 and tau y z as 1.333. Similar calculations can be repeated for element 2, element 3, element 4. Basically, we need to substitute the stress potential values at all the 3 nodes of element into the relation between shear stress components and stress potential in terms of derivatives of finite element shape functions and the nodal values of stress potential that we already looked at. So, once we have the stresses, we can also similarly calculate torque Torque is basically 2 times the area of triangle times average value of stress potential in each of the element. So, for element 1, stress potential average is phi 1 plus phi 2 plus phi 5 divided by 3, that times 2a, that gives us 2.667. Similarly, for element 2, element 3 and element 4. So, we have the torque values for each of the elements 1, 2, 3, 4. So, total torque is going to be sum of all these torques for each of the elements. So, total torque for the quarter model is given by this one. And since only a quarter of bar was modeled, for the entire bar, torque is 4 times the value, that is 4 times 7.112. It turns out that it is 28.45 Newton meter. Also, this problem can be solved exactly. The exact solution is 36 Newton meter, and if we compare with the value that we obtained 28.45 Newton meter with 36 Newton meter, it can be noticed that there is 21% error, and that is because we used only, first of all we used only linear elements, and that too we used only 4 linear elements. So, now let us repeat this calculation by dividing the quarter model into 8 triangle elements. So, this is a finite element mesh, and the procedure is same for each of the elements. All elements are identical for each of the elements. Once we write element equations for one of the elements, element equations are going to be identical for all the 8 elements, and applying the essential boundary condition that nodes, the stress potential value for the nodes on the boundary is equal to 0, that is phi 7, phi 8, phi 9, phi 6 and phi 3, the stress potential values are 0. So, applying those boundary conditions, we can solve for the stress potential value phi at all rest of the nodes, and then we can interpolate, and then we can find the stresses and torque as we did for 4 element solution. And once we do that, and if we plot the stress function contours, they look like this for 8 element solution, and components of stresses, stress contours, tau xz contours, tau yz contours. Similar to that we did for 4 element solution, we can calculate torque for each of the elements, and then we can find the total torque for the entire square bar, and the total torque when 8 elements are adapted turns out to be 26.67 Newton meter, and the calculation is also repeated by taking 32 elements, and the finite element discretization is shown. Everything is similar since all elements are identical. Finite element shape functions or finite element equations are going to be same for all elements, and again applying the condition that stress potential value along the boundary is equal to 0, and we get the reduced equation system. Solving those equations, we get the stress potential at other nodes, and then we can do interpolation for calculations of stresses and torque, and the stress function contours are given here. And shear stress components tau x z, tau y z contours are given here. The total torque for 32 element solution turns out to be 34.26. So, we can see that solution is converging as we increase the number of elements from 4 to 8 to 32. Similarly, but only thing is, as the number of elements are increased, it is going to be difficult to do hand calculations. We need to automate it, and we can write a computer code to do more refined finite element calculations using the automated code. So, here 128 element solution is shown. A 128 element solution gives torque 35.34 Newton meter, whereas the exact value is 36 Newton meter. And so, basically the solution is converged or it is converging. So, the finite element equations that we developed are correct. So, this is the way we can develop finite element equations for any two dimensional general two dimensional boundary value problem. Once we identify the corresponding coefficients k x, k y, p q, and identify the corresponding coefficient associated with essential boundary conditions.